Hi, everybody. Welcome to spring 2022 physics. Sorry I can't be with you today. I'm actually on my way home from Austin, Texas. So I will join you guys tomorrow on Tuesday to teach you some more physics. But today I just have this video lesson for you guys. Just take notes, and then we have some problems at the end I want you to work on, okay? So we're going to be looking at data over the next week or so, and how do you know when you look at a graph what type of relationship the two quantities that you're graphing, how can you determine the relationship? So we're going to get into this, okay? And so there's one type of relationship that we've seen, and we'll see some more, and it happens a lot in science classes, and that's called direct variation. And then sometimes it's called directly proportional to. And so the relationships will always look like this, okay? So it'll be some y, some quantity we're measuring is equal to a constant times x. That would be direct variation. Another example would be y equals a constant k times x squared, y equals k times x cubed, y equals k times the square root of x, y equals k times the cube root of x. So it's always going to be some constant times either x or a power of x or a root of x, okay? It's always going to look like that, all right? And we call this k is a constant. And it's called the proportionality constant. So proportionality. And some people also call it the constant of proportionality. So you're going to see it said different ways. And we need this in order to do our next lab, okay? So we're going to look at relationships between force, mass, and acceleration. And if you recall from before Christmas break, I talked about this. I said, this is directly proportional to, and I said something else, okay? And so we're going to get into more of that language, right? So you understand how to say the relationship between them, okay? So let's talk about the language of direct variation, and how do we take the language, how somebody says something, and then how do we write these, like one of these equations, okay? So let's go to that next. So what I want you to understand next is this language, and if we say y varies directly with x, or if we say y is directly proportional to x, we're actually saying the same thing, all right? And so both of these translate into, we know that y is equal to k, that constant proportionality k times x, all right? And so that's what that means when we see y varies directly with x. So they're just telling you these two, this is how they're related, okay? And so let's look at this next one. Y varies directly with the square of x. So the square of x is really, this means x squared, okay? So y is directly proportional to the square of x. So both these are saying the same thing. That's why I have them together. And what that means is we could write the relationship y equals k times and x squared. So that's how we would say this relationship is, we would say y varies directly with the square of x, or y is directly proportional to the square of x. All right, so this next one, y varies directly with the cube of x, or y is directly proportional to the cube of x. They're saying the same thing, and cubing is just a third power. So that's going to look like this. Y is equal to some constant k times x cubed. All right. And then the last one I want to do is this one. Okay, y varies directly with the square root of x, or y is directly proportional to the square root of x. Those look the same, okay? Those are telling us the same thing. They're telling us that y is equal to some constant k times the square root of x. And so we could also have cube root or fourth root. We could have different roots all right, or different powers, okay? But it's always going to be k times x to a positive power, okay? That's when you have this direct variation, okay? So the next thing I want to do is go into, okay, so what is the graph of all of these relationships? What do they all have in common? And they have a couple features that they all of them have in common. And let's talk about that. So let's turn our page and let's go to talk about that. So what I want to do is look at these graphs and what are the features that cause us to know it's direct variation, okay? And so one of the ways that we know is there's two features of it, okay? When it's direct variation, the graph will pass through the origin. Has to do that, okay? So the graph will pass through the origin. And what I mean by origin, if you don't remember that, that's the 0.00. Okay, so if it doesn't go through the origin, then it's not direct variation, okay? The other thing that happens is as x increases, y also increases. So as x, which is also called the independent variable, okay? So as the independent variable, which in this case we're calling it x, as that increases, I should put as x increases, the y or dependent variable also increases. So this is one of those features that if you increase one, the other one will increase, okay? So if you look at this first graph, all right, as x increases, the y is also increasing. You can tell because this graph is increasing overall, right? It's going up, right? So these graphs will always go up, and it also goes to the origin. So this is an example of direct variation. Variation, spelled it wrong. Okay, so that's direct variation. It's as x increases, y is also increasing, and it goes to the origin. Okay, this one right here, it's also as x increases, y increases, and it also goes through the origin. So this is also direct variation because it goes to the origin, and as x increases, y also increases. Okay, same thing with this one. Okay, and if you know your parent graphs, okay, then some of these make sense, and you go, okay, I know that some of the parent graphs, some, not all, but some of them are direct variation, okay? So this one right here is direct variation because it's increasing. As x increases, y is also going up, right? As you go to the right, y goes up. That's increasing, okay? So this is also direct variation. This one, and it goes to the origin, this one is not direct variation. Now, as x increases, y also increases. So they're both increasing, but the problem is it's not going through the origin, okay? So this is not direct variation. And it's because graph doesn't pass through the origin. So it's not going, it needs to go through that point right there, 0, 0. Okay. This next last one down here at the bottom, okay, is also not direct variation because it's not going through 0, 0. Also, as x increasing, y decreases. So that's another reason why it's not direct variation. So when we collect data, we need to look at the data and realize, oh, that's direct variation. And there's another type of variation that I'll talk about tomorrow on Tuesday that we'll go more into. So another type of variation that's not direct, okay? So this one is not direct variation. Graph doesn't go through origin. So it doesn't go through 0, 0, or doesn't pass through 0, 0. And as x increases, y decreases. Okay. So I want you to be able to look at graphs and go, oh, I can tell by the graph that's direct variation. You may not know the type. You might not know that, y varies directly with x, y varies directly with x squared. That's actually what we're going to get into on Thursday more. Okay. All right. So then the next thing is, okay, so how do we find it from a description? How do we find this constant of proportionality? Okay. So that's what I want to do on the next two problems. Okay. So on this next problem, I'm telling you y varies directly with the cube of x. Okay. So y varies directly cube of x. So from that, okay, we're going to find, and we also know this, y is 72.9 when x is 3. So we have an input and an output, and that's going to allow us to find the proportionality constant, or constant of proportionality, okay? So from this, y varies directly with the cube of x. When you know that, your equation is going to look like this. Y is equal to k times, and it's going to be x, and what are we going to do to x? We're going to cube it. So we're going to raise it to the third power. Now we want to find the constant of proportionality. So I'm going to label this part A, okay? And what we want to do is to find that, we want to solve this equation right here for k. So what we're going to do is to solve this for k, we're just going to divide each side by x cubed, and we get y divided by x cubed is equal to k. So k will always be whatever our y value is divided by our x cubed in this particular problem. Okay, so that's going to allow us, because we have an x and a y that go together. So that's going to allow us to say, okay, so we know from this formula that k is going to equal my y, which is 72.9, divided by my x and cubed. So that's going to be 3 cubed. So I'm going to grab my calculator, because I don't know what that is off the top of my head, and I don't expect you to either. We're going to take our 72.9. I haven't started this in a while. Okay, so 72, we get that fraction bar, take 72 and divide it by, whoops, that's what the fraction bar is for, right? 72, and we're going to divide by 3 cubed. And so we get, you know what? Hold on. That's not what we should be getting. Okay, so let me start over again. Because fraction bar, I had it in a setting that was giving me the wrong answer. Okay, so 72.9 over 3 cubed. Okay, and we get 2.7. Okay, so that's our constant of proportionality. We know it's 2.7. So now because of that, we can write the relationship. So now because of that, we know that y, the particular relationship here is y is equal to 2.7 times x cubed. And then the part C is, I want to determine the value of y when x is 4.7. So then the next thing is, okay, so that means y is equal to 2.7 times 4.7 cubed. And we're just going to put that into our calculator and we'll have it. Okay. So 2.7 times 4.7, and then raise it to the third power. And that's what we should have on our calculator. And we get 280.322. And you can go to like 2 decimal places, 280.32. I'm just going to go ahead and write all the decimal places. So 3, 2, 2, 1. Okay. So that's our first problem. You're going to have some problems like this for the assignment today. Okay. All right. So can you take what's been written and translate that into a math equation? And then using that equation, can you get your constant of proportionality? Okay. So that's what I want you to be able to do today. All right. The next one is really the same thing, but instead of having y and x, it's actually going to be quantities like force and acceleration and stuff like that. Okay. So for this next example, okay, and this is a true statement here. Okay, this is from science. The distance an object falls from rest is directly proportional to the square of the time in which the object has fallen. After 1.5 seconds, an object has fallen 11.025 meters. So this is a distance it's fallen, and this is the time it has been falling, okay? So we want to find the constant proportionality. We're going to use D for distance, okay? So distance an object falls is directly proportional to square of the time. So that's telling us that we're going to use D for distance and T for time. Okay, so that's telling us that the distance an object falls is equal to K times T, but it's not just T, it's the square of the time, so it'd be T squared. Okay, so then part A, we want to find the constant of proportionality. So we can do that by solving this for K. So we're going to take the D and we're going to divide both sides by this T squared. So D divided by T squared would equal our constant of proportionality. And we have a distance and we have a time. So that means our K would be 11.025 meters divided by 1.5 seconds. And we're going to square that, right? Okay. So you wouldn't have to have the units on this, okay? So this would be, I'm going to go to my fraction bar. Let me pull the calculator out, okay? So 11.025 divided by, and then 1.5 squared. And so we get 4.9. So K is 4.9. Our constant of proportionality is 4.9. All right. So now because we know that, we can write our relationship, and it's going to be D is equal to 4.9 T squared. So that's putting in, replacing the K with what it is, 4.9 in this problem, okay? By the way, should notice that's half of 9.8, right? So that's where this is coming from, okay? 9.8 meters per second squared is the acceleration of gravity. This is 4.9 because one of our formulas, remember those 5 equations that we used right before break? One of them was 1/2 AT squared, and that's where this comes from, right? So here's the question: how far has the object fallen after 3.4 seconds? So for part C, that means D would be 4.9 times 3.4 squared, and that would be in meters. Okay, so 4.9 and then times 3.4 squared. And so we get 56.644. And that would be in meters because our distance unit is in meters. All right. And that's how you do these problems, guys, is there's 3 parts to it. I want you to find the constant proportionality. I want you to write the relationship and then tell me, I'm going to give you the input value and you tell me the output value for that particular one. Okay. And that's what I want you to do. And then I have some graphs for you to tell me from the graph, can you tell me if it's direct variation or not and explain why it is or it isn't. All right. All right, guys, that's it. I will see you guys tomorrow. And tomorrow we're going to talk about inverse variation. So there's those 2 different types of variation, direct variation and inverse variation. Okay. And these are used a lot in science classes to describe relationships between 2 quantities. All right. Okay, guys, that's it.